for the conference. As some of you know, I just joined this community back in 2020, and every time I come to this conference, I love it. Just the amount of conversation, and we're all kind of building on each other's presentations and questions that come out of it. So thank you for having me as well. In fact, I'm hoping that everyone seems to say I can skip a few slides because somebody else talked about it. So we have a nilpotent matrix eventually. Maybe after my talk, everyone can just say, okay, we've talked about everything we can. Zero slides. Okay, great. So this is our supercomputer center. It's beautiful view over the San Francisco Bay. That's the UC Berkeley Campanile campus down below. Come visit. Hopefully we can host. Our current political situation doesn't make that so certain, but we would love to have folks in the Bay Area for one of the conferences. All right, so I'll try to hurry up.
That's a good idea.
I appreciate that. If you could talk to my government, I would appreciate that. Okay, so my daughter, and apologies to a few of you, Sebastian in particular saw a good chunk of these slides. I added a few new things, so you can't fall asleep. I'm trying to build on previous discussions a little bit too. So TLDR, my daughter always says, make sure you get at least 1 point in there. Low order splitting methods go all the way back to the 50s. I've just discovered integral deferred corrections as of about a year ago, and have been using them together to create higher order methods. And that gives us a lot more parallelism, especially for the solves themselves. And then faster and more accurate solvers as well. So I am more of a spatial discretization person. I still struggle calculating the stability polynomials for a lot of different problems. In fact, I had a great one where it was unstable at every wavelength except constants. That was pretty good. But I work with adaptive mesh refinement. And so everything I look at, especially for hyperbolic problems, creates issues with time integrators. So operator splitting, a little review there, but I'm going to go through it really fast. So this crowd knows all about that stuff. And then specifically how we're using integral deferred corrections and some of the parallelism there with these operator splittings on GPUs, because that is kind of our target. A bunch of collaborators, my awesome productive postdoc Nate just left for AMD. He's also productive in a different way. And then some collaborators, and then for some of the software we use that, I also have collaborators at University of Virginia. So, and I have to thank our sponsors, funders. At least for this year, we still have money from them. We'll see how that goes.
But maybe the TLDR, it's too long, didn't read, right?
Yeah. Sorry, I should have pointed that out. Who knows what TLDR stands for? And what
everybody knows.
Age skew of that. All right. So thank you for introducing rotating shallow water equations. Very helpful. I don't have to talk about it now. Finite volume methods on a cubed sphere. And this is with 2 levels of 4x refinement. So this is doing a local time stepping with the refinement. So if you want to see tropical cyclones interacting to help predict their paths and to see who's in the path of devastation, you need mesh refinement in addition to good models to start with and a lot of data. So it's 4th order in space and time. And that local time stepping is what I'm going to get into a little bit. The tagging we use it's a dark art. You can tag based on magnitude, gradients, Richardson extrapolation. Don't ask me about it. You can do all kinds of things. So in terms of what would be considered single global time stepping for AMR, it has some good and bad properties, but basically the gray is a coarse cell. You take a big time step. Finer cells still take a big time step relative to the CFL for that grid spacing. And then you have these synchronizations, right? Just like you do with any serial time integrator, and off you go. So you're marching all of the grid all at once, regardless of its spatial resolution. And so what's good and bad? Load balancing is super easy, right? It's like you're never concerned about how much time something takes. It's all just about, is it stable and how many kind of degrees of freedom. Somebody said DOFs earlier. I thought that was brilliant. I've never heard of DOFs before. So coarse versus fine CFL is the issue though, because as you know, these methods have very different dispersion properties and dissipation properties at the different CFLs for that grid spacing. And then, so, great, put a parabolic problem in there. You don't care about fine features anyway, just run it through. For local time stepping, that's kind of what it looks like. You take a giant time step, right? Because remember, this one's limited by the CFL of the finest grid you have, if it's an explicit method, or if you want to get the resolution tuned into the method. I'm a big fan of doing spatial discretization and temporal discretization together. A lot of people in climate and weather love that because you get the properties you want, and then refinement doesn't affect you as much. So here on a coarse grid, you take a giant time step, synchronize point, take two finer time steps on the next grid down, which means I do one fine and then provide boundary conditions for the finest. So you can see this is a serial dependency. It cascades down through the hierarchy. For astrophysics problems, people will do 20 AMR hierarchies deep because you're talking about such huge scales, right? And so these steps kind of become serialized, and then load balancing can be a big issue if you've got a dynamic mesh refinement. It's moving around physically in space. You're adding mesh here, removing it there. So that becomes a little trickier. And all of these kind of red bar synchronization points happen because there's a synchronization between what you just computed and what you need for boundary conditions for the next section. So that can become a bottleneck. In fact, for some of the deeper AMR hierarchies, they go back to local time stepping because it's just not profitable anymore because you lose your scaling. And so these, oops, sorry. Typically these are best. Can you see the laser pointer? I'm hoping, okay. Are best for hyperbolic problems because every one of these grids has a fixed UFL, right? It is all the dispersion properties, everything we want happening at the correct level for each of these subcycled grids. All right, so given that, here's a typical grid spacing, vertical grid spacing for like a climate code. I think this came out of E3SM. If you refine it, you end up with effectively paper thin grid spacing. So a cell in a typical climate code at maybe 10-kilometer resolution looks like a piece of paper near the boundary layer at the bottom. Look, because it's 10 kilometers wide and maybe 10 meters thick, right? So this is horrible. I burned myself and some embarrassing funding on a problem like this, and people in the field know that you do horizontal explicit because it's cheaper, not as globally coupled, vertical implicit because of the stiffness of this problem in particular. And so I was using fourth order additive Runge-Kutta L-stable 6-stage methods. Looks something like this, right? Implicit scheme, explicit scheme. They're all coupled every stage, very serial in terms of how you have to evaluate things. Every one of those stages looks like kind of a global communication to get your Go cells set up, do all the explicit stuff in the horizontal directions. In the vertical direction, you've got a CFL anywhere from 4 to 100, depending on your horizontal spacing and your vertical mesh. And so it's stiff and it's hyperbolic, right? So how do we do with stiff hyperbolic problems? That's one of the, thank you, Thibaut, for having introduced the question of what do you do when you have large CFLs and imaginary problems. So that global step AMR part is kind of the issue here. And so, you know, if you want to solve this in the vertical direction, there are great talk about how to go after some of that with, you know, the implicit system, parareal, but it's nice because it's globally parallelized, right? You're solving batch vertical columns every time you need to. So this would be the anatomy of the sub-cycled version. So serialized, start with the old solution, take a time step on the coarse grid, new coarse grid solution, back up, do this course define interpolation to provide boundary conditions and to potentially initialize new patches. And so, you know, every one of these red dots is that complicated IMEX scheme. Has to do global communication, has to do the vertical solves. And so that time step is kind of nested. And this is only a factor of 2 refinement. If it was factor of 4 refinement, I'd have 4 steps before I could take the next course one. Or on the fine grid here, 16 steps, et cetera, et cetera. So if I had 4 or 5 nested AMR hierarchies, we're talking about a lot of bottleneck before I can even move the solution forward at all. There's this space-time ghost cell problem where you're providing time-dependent boundary conditions on the edges of your finer meshes. The subcycling kind of is recursive that way, more communication between these things. Typically, we co-locate the finer meshes on top of the coarse ones, but that has its limits in terms of the number of total domains you have. Sometimes you do like a multi-grid consolidation on the coarse level to get more of those parts communicating or avoiding communication. And then there are these conservation fixes that we have to do to make sure that anytime we calculate solutions on the fine level, they're not out of sync with the coarse levels. So this is complicated, right? This is like each one of these things looks a little bit like a global communication, and it's all, in the end, it's serialized, right? Do this, then this, then this, then this, then this. So it doesn't give you the parallelism you would want. Time. So guess what I thought about doing, parallel time. To unwind a little bit, I love how we are now talking about hyperbolics. Remember 5 years ago, we were talking about parabolics and how it didn't work for hyperbolics yet. I think we're coming around. It's really great. So this would be, for example, if I was going to use an backward Euler with a fourth order center difference in space. A lot of climate codes use these center differences. Spectral methods come out to look like center differences in some ways. So at a CFL, sorry, this is meant to be implicit, not explicit. I didn't mean that. You see the dissipation, right? No, wait, that is explicit for CFL 0.9. And, not many points per wavelength for this square wave problem, but if it goes around once, that's what it looks like. Little dissipation, not too bad. And that's mostly because, forward Euler explicit sorry, I think that's RK4. It's not super dissipative, but when you have backward Euler, working with fourth order center differences, trying to double your CFL, it's horrible, right? And that was your plot effectively. Like when you do backward Euler as a preconditioner for a single step, your spectrum screwed up. You're getting basically only one mode correct. And if you look at the spectrum, this would be the unit circle for perfect imaginary advection transport. Your implicit Euler is getting one mode correct, and the rest of them are horribly dissipated, even at CFL of 1 effectively. And once you're up at CFL of 4, which would be the minimum I can do for a vertical thing, you've got effectively these problems where most of your content is gone, right? It dies immediately, which means that I don't have a square wave. I have, one mode vertically in the atmosphere. Climate codes like that sometimes because you're trying to get rid of these fast vertical waves. But remember, I've got a local boundary condition calculated at a different CFL in time, right, next to my current finer mesh, nested ad nauseum. So if, CFL 1 looks good, looked bad, CFL 4 next to it looks like the wave is inverted, right? The phases are way out of whack. You've lost the content. Those boundary conditions are crap. So I spent about 3 months trying to fix this for, full 3D global AMR climate simulations. And I just didn't make any progress by the time the project was over. So that's a bummer for me. I would have loved to have had AMR for a global climate model. Anyway, so lose-lose situation. So I went back and did the analysis on this, and I started realizing that what you want is spectral accuracy for a range of CFLs. And in particular, we all, in our field, we give up on 2 delta X modes. They're not physical. They don't represent anything. Best thing to do is dissipate them typically. So you see hyperviscosities and stuff like that. 4 delta X modes, again, fairly nonsensical. You're not going to resolve them in any way that you get decent accuracy out of it. So across the bottom, it's basically what's the wave number. And if you thought 8 delta X modes, right? So 8 points per wavelength, and then the lowest wavelength, which is 1 wavelength over the entire domain. If I could somehow get the accuracy up to 10 to the minus third relative error just for those waves, that's what would have been a CFL of 4 squish, or a refinement ratio of 4 squish. Because remember, all of these up, right? Oh, my laser gave out. No, okay. All of these up here are aliased out if I do a 4x coarsening, right? I can't have any of that content if I'm looking at the coarse grid, because effectively I'm sorry, if I'm looking at the fine grid, effectively it's going to contaminate my coarse grid, right? So, and that little dot right there is, 10 to the third minus relative error, and the dashed line is phase errors, and the solid line is amplitude errors. So even RK4 with center differences, which is a pretty good fit, right? It's pretty typical in a lot of codes. You're not getting good phase representation. You're actually getting around 1% errors for those 8 delta X modes, but you're doing pretty good on effectively a CFL of 1 or the amplitude error. So that's the target, right? That's just one level of refinement. Now I need to do that potentially for 2 or 3 or 4 refinements as I propagate closer and closer. So anyway, just other examples. If you did it with implicit Euler, you're getting no waves correct. So that doesn't work. CFL of 4 makes that very bad, and that's what we saw in the spectrum. So that 10 to the minus third relative error is basically you get one mode, if you're lucky. So if you want to actually get all of those modes about right, this is about as close as I got with something fairly complicated. So an implicit Hermite integrator. So that's where you take the Jacobian at the old time and the new time, and you include that to improve the accuracy of your method. So it's fourth order kind of cubic spline accurate. And then you do one extrapolation of that. So half the time step, do two of those time steps and combine the results. You can show Hare and Vonner, thank you for bringing that up, that's one extrapolation is stable. After that, you lose a stability right away. And so you got an eighth order method with a seventh order upwind and spaced. So you get a little dissipation and you're getting close. Your amplitude errors are great, right? Your phase is good. And I could use that absolutely without contaminating my fine grit solution. So that would be an example of what you might want to do if you could get, and this is easy to do as a method in 1D. It's horrible to do in 2D, right? Because you're carrying the Jacobians around, you're solving these implicit systems for a nonlinear problem. So that's why I lean on splitting as potentially the way of getting that data. I'm going to really speed up here because this is more of the computational stuff. We've talked a lot about low order versus high order methods. We talked about Perlmutter. Thank you for bringing up A100 GPUs. We just announced that we're going to get a Vera Rubin machine, right? Super excited about that. I hope I'm allowed on it. I hope I have funding when they get it. And communication is so much more expensive. So whenever you get data across the wire to your GPU, you better chew on it to get everything you get out of it. And in my opinion, that should be accuracy. So if somebody says, oh, I'd love for you to do backward Euler with, fourth order center differences for my hyperbolic problem, I'm going to propose new time integration methods and new spatial discretizations and a bunch of other things to try to dissuade them, because otherwise it's a waste, right? Okay, so one of the things we did in terms of memory layouts is go from typical striped, lexicographical ordering to something called bricks. This allows us to kind of virtual map on the memory. Stencil equations are much faster as a result. So on a lot of these machines, the latency is the problem, not the bandwidth. So bigger ghost zone exchanges, no big deal. Do layouts so that you're communicating one big fat message to neighbors as much as possible. Extra exchanges so that you can avoid a communication because the latency kills you, not the bandwidth. So some techniques there with this brick layout. Stencils on the roof line. Somebody else talked about arithmetic intensity. I'm trying to remember. So that's what this plot is. We look at, our stencil operations and they're kind of that speed of light, they're memory bandwidth bound. If you do something as big as like 125 point stencil, Stellan stencils, you can get like a 12th order method out of that, for example, in 3D. If as long as you're close to that roof line, you're getting basically the same time to solution, no matter what the order of accuracy. Wow. So why not go for the higher order accuracy, right? But it takes some code generation to get that performance. But it's a 10x difference in terms of the flops you can get. And why not use those flops for accuracy? So that's kind of my argument in general. And this says don't do sparse matrix operations if you can avoid them. Okay, high order methods for efficiency, avoid zero bottlenecks to get more bandwidth, more parallelism, and then efficient parallel solvers, which ends up being operator splitting and batch solvers on GPUs. All right, so moving quickly. I love coming here because I keep up to date with what's going on. Now I'm super interested in some of the modifications for diagonal preconditioning. I'm looking forward to Rob's talk on hyperbolics in XBraid and MGRIT. I love that they're in libraries, so I can try them out more easily. I hate having to code things up from papers. It's hard. It's error prone. So thank you again for involving me. Whole bunch of other things that I haven't seen yet, though. Last time we had one of these, somebody was talking about space-time DG. I have colleagues that do it. It's very nice for moving boundaries. Splitting methods, I'll talk about it a little bit here, but like Ray Spiteri, if anyone knows him, University of Saskatchewan, he does a lot of splitting stuff and is being very innovative with it recently. So I'm trying to collaborate with him a little bit. Extrapolation methods, I bet people hadn't heard about those in a while. So I've been using them piecewise in order to get higher order accurate values. And then there's a whole bunch, I can't believe the time integrator community is having a revival right now, but even in Runge-Kutta schemes, there are multi-rates, there are infinitesimal multi-rates, peer RK schemes, GLMs, generalized linear methods. There's a lot of stuff going on still in just the pure time integrator community. So anyway, what I want to look at is a simple splitting operation, typical, exponential splittings, where these are approximated by some kind of RK or other method, exponential matrix operations, and then parallel deferred corrections, which luckily has been introduced. So you do a predictor, accumulate values, try to get higher order accuracy as you accumulate them. And that was all Andrew Kreisli, Ben Ong, and a few other people. So this is what happens if you do strength splitting with simple homogeneous Dirichlet boundary conditions for the Poisson problem. Love it. Thank you, Martin, for introducing that to everyone. Let's keep our boundary conditions 0 all the time. The problem is that in AMR, I always have time-dependent boundary conditions. And if you include those in strength splitting, you get crap. Notice the order of magnitude. This is a log scale, right? So 10 to the minus 9th errors. I'm screwed up. 10 to the minus 2 errors. And it contaminates the solution everywhere near the boundary. You're still doing great in the interior, but the boundaries are messed up for time-dependent DCs. So again, I tried splitting in an AMR hierarchy after 2 months of debugging and trying to figure out the problems. Boom, the issue is the splitting doesn't do time-dependent boundary conditions.
There are fixes to this.
There are
The Austrian school.
Yeah, I've looked at that. First order fixes, second order fixes,
So you want high order.
higher order fixes, and I think actually Riddick is going to give me the higher order fixes I want. I'll get to that in a second. So linear model equations. If you look at how those boundary conditions, suppose I just move it into the right hand side. So I take a nice linear operator, any inhomogeneous boundary conditions I treat as a source term that's time dependent. And, if I have cosine at the boundaries, it's going to be your example from, Neumann boundary conditions effectively. And then you run it through and what do you see? So Taylor series expansion, first derivative, got that in the Taylor series. That's just consistency, right? Second derivative, you get this interesting mix of things just from the B tree, right? Following it through. And then why is the convergence for these things poor? Well, it turns out for this like a Laplacian with a decently large grid, small grid spacing, just for one of the modes, right? This is the smoothest mode. That operator is 10 to the 10th, right? H to the 4th, plus the Laplacian times the eigenvalues. And you're trying to get it to cancel with your time-dependent boundary condition on the same order. And then if you get that right, now you're trying to get the time derivative of your boundary condition correct at 4 orders smaller. So, on a log plot, this looks like hell, right? It's like, these two things canceling way up here. Whoo, I got those to cancel. I could use different operators, different quadratures, whatever it is, right? And I still have 4 orders of magnitude to go to get that next term, just for the constant in the second order term to be small enough to be comparable to the interior truncation solution errors. And this is really just in those boundary cells because it looks like a delta function on the boundary that's not coordinated with the operator or the time evolution. So, okay, again, now I've got it to second order, but at least I understand where those giant errors are coming from. And if you look at why we get away with this stuff for low order methods like backward Euler, the terms are all there with the right scaling, but the constant's wrong. That should be a half in the Taylor series expansion, right? And then for Crank-Nicholson, if you center this incorrectly, if you think, oh, I'm just going to do implicit midpoint for that boundary condition, you're screwed. Again, bounces back up to 10 to the 8th kind of relative errors on those constant. It has to be centered with the operators. So that's why implicit RK schemes, diagonally implicit RK schemes, when you carry the boundary condition with the operator, you do a lot better on these things, as opposed to making some quadrature estimate of it. So I'm curious to see how Riddick does with, what SDC and some of the other methods do with time varying boundary conditions to understand like where is that time accuracy versus the representations of the boundary conditions on course time intervals. How do those two things play together? Numerical boundary layers is what they get called sometimes. All right, so then there is, this exact analytical solution for a linear operator. Look at it, and what it turns out is that, whatever quadrature you use for this integral, super sensitive to that. So if people are interested in going into this, I'd love to talk about it with you, but basically, you could try to make it consistent to some higher order, but if you're not doing exactly right to match the exponential evolution of the solution, then you're going to end up with these higher order terms in the B tree, basically. This is just 1D. I haven't even introduced splitting errors in this problem yet. Okay, so Riddick, part 3, sorry. So integral deferred corrections starts with a residual and an error. Looks at the time evolution equation for the error, does a bunch of substitutions. You end up solving for some Q variable, which is a combination of error and residual integrated. Let's just call that E plus V. And then boom, you have a new ODE or system of ODEs where your old solution, your approximate solution gets modified and you're solving for that in time. So this is true whether it's explicit or implicit or whatever. This is just substituting things into it. And the difference between SDC is that this is done as a quadrature over time. In our IDC, it's done as a polynomial interpolant of previous solutions. So almost like multi-step versus RK. What's good about that is there are lots of ways to get higher order accuracy with those interpolants. And the question really is stability. And don't ask me, I'm still trying to figure it out. But for the predictor, you get this, residual equation. And then for Crank-Nicholson, it just looks like this. Again, this Q variable is now treated implicitly with a modified right-hand side, which is our G. And as a result of doing that, and you've already calculated this one, right? If you're looking at the same time steps, this is done already. So really, it's just one more function evaluation. And then you do a quick get a solution, do a quick update to these values. This is just a quadrature on your right-hand side evaluations, right? And so you end up kind of including this extra source term. And what's bonus though is that it's homogeneous boundary conditions, right? So you're eliminating everything you had from the original operator, but as it's the error equation, it's homogeneous boundary conditions. So splitting works much better now. I don't have these huge error constants from the boundary condition treatment. So just real quick, simple splitting has been around forever. A lot of people do it. Cheap solves, 1D don't require a lot of iterations or any. Can use banded solvers, stuff like that. What's bad is that if you want fourth order methods, it's, for two operators, it's 7 stages with negative time steps outside your domain, right? But not great. Strength splitting, I add more operators, 3D, advection, diffusion, reaction, whatever. Pretty soon I've got 19 serialized solves just for second order, right? So each solve might be simpler, but as a result, it's a lot of serialized work. Multiplicative splitting, you can do that, but it is serial. You can do additive splitting as well, but it's very hard to keep L and A stability. So this is kind of a big, if you're a stability function junkie, this is fun, right? But for me, I just want to do an application solution. So basically and every time you add boundary conditions, nonlinear source terms, like the splitting operations become even harder. So if people have magical insights into that, I'd be open to it. For the deferred correction stuff, this particular form of it, it's nice that it, is equally spaced time steps, inherits the stability of the base methods. Pointed out, you can do kind of a pipelining wavefront solve for these things. And this is the important one, that with evenly spaced points, I don't know if this is true with SDC, with evenly spaced points, you get the order of the accuracy of the base method every time you do iteration. And I'll show you a couple of magical charts that prove that. You do have a lot of extra memory you're carrying around for this multi-step interpolant, basically. And then is it okay to not do an exact operator? Can you do a split operator? So quickly, advection diffusion, first order splitting as my predictor method. So you do a correction with more points, right? Boom, first order, second order, third order, fourth order. So pretty nice to be able to get that very quickly. And, it's backward Euler effectively for that predictor. So you end up with a stability, L stability all the way through to the fourth order method. Which you would also get if you did extrapolation methods, which give you some parallelism there too, right? Because fourth order extrapolation method for backward Euler would be fourth order, 4 stages or 4 parallel evaluations, but not well balanced. Second order strang splitting, this issue, I fixed that, but it was kind of a bad interpolant that was not well behaved at what would be second, fourth, sixth, eighth order. So you start running into the kind of Lagrange interpolant problems with this if you're not careful. And there's actually a great paper by Trefethen, for any of you that are doing Lagrange interpolants. Arnaldi Vandermonde is the title of the paper. It's using kind of a orthogonal factorization on a Vandermonde matrix that gives you 20th order Lagrange interpolants if you want them all. Very stable. So here's our, thank you, Dahlquist scalar test problem, except this one's oscillatory and it's very little damping. You see the amplitude changes a little bit there. I think this is like 0.1% damping or something, which is, I think it's a good way to have a little diffusion in there. And this is what Riddick does, you know, second order, fourth order. This is a log scale, right? Sixth order, eighth order. I mean, it just keeps going. So I'm really liking this method right now. It's, yes, it has a lot of extra memory involved, but if you carefully assemble things, you can get very rapid convergence in time. And it's not iterative, right? This is one pass on the time integrator. So that says something. So quickly go through these. So Crank-Nicholson with an eighth order spatial discretization, predictor corrector for both of those. Boom, 2 passes, sixth order. Error analysis for splitting. I won't go into it, but basically, you know, you can, for linear problems, you can kind of see what's happening with the correctors. And it only grows from the residual of the error. It doesn't grow from, like, if you start with 0 error, then you end up with only accumulating a higher order in the time integrator error. So that's nice. It's kind of like an exponential Rosenbrock scheme that way. But they need to cancel to higher order to make sure it happens. So you have to be very careful about how you do this kind of effectively residual quadrature. So if it's nonlinear, again, I don't like doing nonlinear strength splitting because it's too hard. So instead, I just do something like a Rosenbrock scheme for nonlinear problems. So you freeze the Jacobian. We talked a little bit about it yesterday. And then you avoid any Newton iterations on this whole thing. You can get L-stable, A-stable options. You can't get good splitting options. There's something where you approximate the Jacobian with operator splitting and it quickly goes to hell. But it is something I'm investigating. So if you only have a couple of terms, like 2 terms, this is a nonlinear viscous Burgers with a very low viscosity. And again, these second order Rosenbrock schemes as the predictor and corrector can converge much faster and much higher order. And very quickly get down to, you know, the kinds of errors everyone else is talking about. And then lastly, I talked about Merstelin stencils. It's where you use the right-hand side to kind of modify your stencil to get higher order accuracy for certain kinds of problems. So if you looked at kind of the same spectrum of things, second order centered differences, you know, it hugs the exact derivative nicely, but as you get to 2 delta X modes, you have horrible kind of computational modes for that. Fourth order doesn't get any better. Compact sixth order, again, you still have those modes. So that's why people do upwinding. That's a fifth order upwinding. If you do a compact fifth order, you can get something that almost looks like spectral accuracy for most of these wave numbers that I care about. Even though it's 1 order lower, it has the exact right dissipation properties you want. But that means you're solving a global problem for the operator output, but it's along grid lines. So again, it's another batch solve in a direction or dimension split way. And if you do it for advection diffusion problems with these splitting methods, I can have aspect ratios of 100 to 1, just like you'd see in a climate code, and I'm doing fine. So I'm now looking at doing this for cube sphere global simulations, especially for larger time steps. So it doesn't matter whether I have 2 to 1 or uniform grid spacing in dx and dy is the vertical direction. I can still get fourth order accuracy, good convergence, and effectively operator splitting still. Okay, work in progress, stuff I'm doing right now that I really want to wrap up. That was this plot I showed you for Riddick convergence. If you combine it with a 2x refined finer grid and do a few more function evaluations, treating the output of the Riddick scheme like a collocation method, and you're able to get, boom, 4 orders more accuracy from 1 refinement and 1 corrector iteration. Still trying to get at the root of this. It's not just, you know, half the grid spacing, or sorry, half the time step and that effect. It's more than that. And I think it's coming from the fact that you get some nice cancellations in the null space of the fine grid operator.
Like a Richardson extrapolation, kind of.
It isn't. That's the thing. It seems to be behaving that way, but maybe under the hood it's going to. I'm not sure. So that's one thing I'm working on. If I do a factor of 4 refinement, this drops down even further. So I'm hoping this holds for more correctors. Like, can you imagine getting 1 more corrector and being down here already? Pretty nice. This is machine learning as a coarse grid propagator, or in this case, the approximate predictor. And it's a little hard to see, sorry. Initial condition, it looks like a wave. It's coming in, it's gonna hit a change in speed of light, and then as a result, it reflects back. So blue, then orange, then green as it crosses the interface, then red as it transmits through and reflects back. Okay. So that's what machine learning can do as a predictor. Pretty good. The errors are around 1%. I can certainly, because Riddick doesn't care what your predictor is. It's just going to make another pass. Okay, done. And this is the spectrum of that solution. Frothing time, it's got some errors and overshoots in the spectrum, but later times it's doing great. Okay, so that's it. I would love to collaborate with people. Here's some of the things I'm interested in. All over the place. I know I focus on applications. I'm not a time integrator guy, but I'm trying to find fast ways to run this stuff on GPUs. And thank you. It's really nice to be here. Should have seen. All right.